What is up, everyone? I am back with another video. It's been quite some time, probably 2 months. Last thing you guys saw was the suspension install and some of the billet angle gear oil pump stuff. I've been pretty busy with work. My day job pays for everything you see in this garage. It pays for my car, it pays for all the tools, pays for all the rent, pays for everything. So that job has to come first. I do software programming every day, and I've been working on a pretty big proof of concept for these past 7 or 8 weeks that has been consuming a lot of time, so that comes first. Been working on a new version of my Vol-Squirt plug-and-play ECU for the 94 through 98 P80s and 960/S90s. This version addresses a couple small bug fixes, nothing really major, but I will be posting updates on that very soon on my Facebook page, Hellmoose Performance LLC, so go look it up. Go like that page and make sure you subscribe for updates on there. I also produced a second billet angle gear that I'll be sharing soon. I'm very excited about. I went to a friend who lives in the Netherlands. He does dirt racing with his Volvo 850 all-wheel drive, and he put together a 5 or 6 minute snippet of what he's been working on, his whole project, the overview and everything. And I'm going to be showing that in another video coming up. I think you guys are really going to like that, and he's going to be doing some testing soon too. Been working on a new Hellmoose Performance LLC website. If you go there now, you'll see it basically just redirects you to my Facebook page. I do software programming all day, so the last thing I want to do at night is more software programming and creating a new website. But I'm going to be working on that very shortly. I want to put all the all-wheel drive swap stuff on there, the Vol-Squirt stuff. Basically, all these products I've been working on, I want to get them up there and get the information about them out there. And lastly, and the most unfortunate, is that I did end up breaking the car 2 months ago, launching at 6,500 RPMs. And instead of making a video saying, oh, it broke, wah, 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 I wanted to, analyze the failure, come up with the solution, produce the solution, test with the solution, and then make a video in one big shot to show the entire process. I think it's gonna make things a lot more clear. So let's get into it and let's see what happened with this thing. It's not that big of a deal, but it took some time to develop a new version of the thing that broke. Let's go. So before we get into why these failed and some improvements on the new version, we need to talk a little bit about heat treating, specifically heat treating steel. First thing we need to talk about is transformation temperature. And this is the temperature that changes the steel's properties. So once you go above that temperature, the steel's properties change, its shape can change, it can warp, it can deflect and whatnot. And there's 3 main heat treating processes that we're going to talk about that pertain to this specific axle design. We have annealing, normalization, and quench and temper, also known as through hardening. So the first type of heat treating is called annealing, and this is when you heat treat the metal. You heat the metal up to its transformation temperature and you let it cool in the oven slowly. So as that oven temp comes down, the pieces temp will come down as well. And this will cause the metal to become very soft. And this is its softest and weakest form. And the reason for doing this is because it makes it machine very easily. For ASI 4340, which is the material I use in these rear billet axle stubs, the hardness is around 17 HRC, which is around 480 megapascals yield. That's not a lot. To compare that, my 7075 T6 aluminum transfer case has the same yield strength, but it is way softer than the steel. So this is why heat treating steel is so awesome, because you can increase the yield drastically 3 or 4 times. The next is normalization. This is when you heat it to the transformation temperature again and you let it air cool. So you take it out of the oven and you let it cool in just ambient air. And what this does is it allows the metal to cool a lot faster, so it becomes harder and stronger than annealed steel. And it's still machinable, but it's not as easy as machining annealed steel. And for AS 4340, usually you normalize to about 40 HRC hardness, which is around 1,000 megapascals yield. Our last one is quench and temper, also known as through hardening. And this is a way to basically get the steel as hard and as strong as possible. And what you do is you heat it to a certain temperature above its transformation temperature, and then you drop it instantly in oil or water so that it cools down pretty much immediately. But what this does is, because it's cooling so fast, it makes the material very, very brittle, almost like a glass kind of brittle, where it could just, if you exceed its yield, it'll just snap, right? Instead of being ductile and twisting or pulling apart. And what you do in order to remove that brittleness and put a little bit more ductility back into the material is you temper it. And this is where you heat it to a certain temperature. There's certain different temperatures you can heat it to, and then you let it air cool. And then basically how hard it will be after is dependent upon what temperature you heat it to and then let it cool to. And it's not machinable using traditional methods, you know, like milling. I guess you could maybe hard turn it. You could hard turn it, but you can't tap it using a regular tap. You can't mill it really. It's hard to work with. And for AISI 4340, you want to target about 48 to 52 HRC for a quench and temper, and that puts the yield at 1600 megapascals compared to 480, almost 4 times as much when you quench and temper this material than its annealed form. Obviously, it's a lot harder to work with quench and tempered material, especially when you involve threads and splines and whatnot. And we'll talk about that a little bit later, but these are the basics you need to know in order to understand why this piece failed and why the new version is much improved. The last thing I want to talk about is case hardening. So case hardening is when you only harden to a certain depth. So through hardening, the entire piece through is going to be that hardness. Case hardening, only a certain depth will be hard. So maybe like 50 thousandths of an inch or something. There's a couple different ways to do this. There's induction hardening, there's nitriding, there's carburization, and the whole point of it is to increase its toughness plus durability on the surface. So this is very good for gears and splines, and in version 1, I used induction hardening, right? And basically that made the splines, the outside surface of the splines, fairly tough and durable, but it left the inside softer because the case hardening does not penetrate all the way through like through hardening. So before we move on, I just wanted to talk a little bit about that too. So with some of that metallurgy background out of the way, now we can finally talk about why exactly these failed. So originally, I wanted to have these pieces manufactured out of through hardened 4340, right? But the issue, I want to have them through hardened to about 40 HRC, so around normalized 4340. The issue with doing that is once you normalize steel, it's pretty hard to cut a spline using a traditional like gear cutter method. So my manufacturer said, you know what? We can't make these out of normalized 4340 and cut the spline. It's too hard. We won't be able to do it. So instead, what we did is we manufactured them out of annealed 4340, which is its softest form, right? Remember, only 480 megapascals yield. And then what they did is they induction hardened the spline. So basically you have like an induction coil that goes down it, and it heats up the metal on the surface, and as it's going down, it's also spraying water on it, and that water is cooling it. And you can see how it looks like burnt kinda? That's from the induction hardening. Now the issue with the induction hardening is it doesn't go very deep. You can see some heat marks here, but in this case, I don't think the induction hardening went nearly as deep as it needed to be. And honestly, it was my first time doing a heat treatment project, and I didn't really specify the case depth because I wasn't really sure. It was kind of a last minute. They're like, hey, we can't do it the way you want it. Do you want us to induction harden? And I was like, all right, sure. Like, we're already on our way, you know, let's get them in, let's test fit them, let's get something working and see where that goes. But you can see the case depth definitely wasn't deep enough, and it also wasn't hard enough. You could see those bite marks right there from its mating side. And you can see the heat, the induction hardening, it was also kind of consistent. Or inconsistent, I'm sorry. And it just, it didn't work that well. And when you're using AISI 4340, it shines when you through hardening it. Inductioning harden it, it's kind of useless, especially for an axle application where you have thousands and thousands of pound-feet going through these things. They have to be really strong. So what happened is the soft anneal core twisted. The core yielded, but the splines stayed in pretty good shape because they were induction hardened. So they were fairly tough and durable, but they definitely could have been much stronger and much more durable. So that was the problem with these, is that I manufactured them out of annealed 4340, the softest material, or the softest form of steel, and then induction hardened the splines to keep the spline strong, but then the core wasn't strong enough to handle the actual torque. So that's what went wrong with these. Another thing to note is this did not happen from locked four-wheel drive. If someone says locked four-wheel drive caused this, I'm gonna lose it. But another thing you see is those bite marks are actually where its mating part length ends. So having the spline extend even longer makes it a little bit weaker too, because you're missing all that material. So you can see it held together where it was clamped in the mating side, but it twisted after. And we're also going to talk about having the splines root diameter on the same operating diameter as the shaft, and why that's a pretty big disadvantage. But annealed 4340 induction hardened splines, no good. 4340 is not a case hardening steel, it's a through hardening steel, and induction harden it is a giant waste. But you know what, revisions happen, and I got a lot of good data out of this. I got to test fit it, I got to make new improvements on the next version, so I can't be mad. I mean, and they came out pretty good, and I made a good relationship with a manufacturer overseas, and they did the second version, and we'll be talking about the second version next and its improvements. So after the failure, I was basically like, well, how the heck am I going to manufacture these things if you can't cut the splines after you heat treat them? Because when you heat treat something, like I said earlier, it distorts. So if you were to if you were to cut the splines and heat treat, the splines are going to move all over the place. The tooth thickness is going to expand. It's not going to fit anymore. So what like OEM manufacturers do is they run a bunch of test pieces. So they run like 4 or 5 test pieces, all with different tooth thicknesses on the spline, and then they heat treat them to the desired, through harden them, quench and temper to the desired hardness, and then they test fit those, or they measure the tooth thickness and see how the tooth thickness changed after. But that's kind of hard to do when you're doing a one-off piece, because it takes a lot of time, it's expensive. Another thing some manufacturers do is they cut the spline, they rough it, and then they through harden it, and then they basically lap the spline. But you need spline lapping tools, and it's even hard to finish machine using a traditional gear cutter. And so like something like that is just completely unfeasible for low quantities or one-off production. So I had to come up with a different method, and my manufacturer helped me, and it turned out pretty darn well. And I'm going to talk about that in the next clip. Before we start talking about the new changes on version 2, I just want to get some footage of them. Absolutely beautiful, beautiful machine work. Look at the light coming off them. It's so cool. It's just such a perfect surface finish that you can get that kind of effect right there. But the spline just came out unbelievable. Unbelievable. So nice. Really happy with how these came back from manufacturing. So since we can't cut the splines once the material's hardened, and we can't cut the splines before hardening because then it's going to distort and not fit anymore, there was really only one way to manufacture this piece. So what I did, or what me and the manufacturer did, is we first rough machined it out of annealed 4340, its softest form. So taking bulk of the material off in its softest form. All the outer diameters we made bigger, and all of the inner diameters we made smaller. So this way, in the next step, we through hardened it to 48 to 52 HRC. So the ODs are going to expand a little bit and the IDs are going to shrink a little bit. That way, after that, because we rough machined it, we have material left that we can go in and we can hard turn some of these diameters down to in spec, and turn some of these IDs larger back into spec. And after that, you basically have this exact piece, but you don't have it with the spline. And I'll show a CAD drawing of this, but pretend there's no spline there, it's just solid. Now what we do is we get this spark erosion machine, and this machine can pretty much cut any hardness. It uses electricity, anything that can conduct, it can cut. And basically we make a counterpart to this spline, and we spark machine that down it to cut the spline. You can cut it at any hardness. And we also did that with the threads. You can get another spark machine insert that will do the threads. So if you look at this, you can see how they were cut. And the cool thing about this is you cut it using a 2D DXF drawing. So I was able to generate the exact spline I needed digitally and have it be geometrically perfect. So it definitely is probably going to make the spline portion stronger, because the spline is going to be a perfect involute curve. It is going to be geometrically perfect. Whereas something like this, where it's gear milled, it gets messy, you know, because you have a piece that's turning and cutting, and then you rotate it through the next one instead of just doing it in one shot and getting everything geometrically perfect. I want to show a little bit more about how soft these are. Get out of here. I was literally able to drill into these with like $1 Amazon drill bit. That's how soft these are. These, you would never be able to drill into these with like a drill bit. Crappy dollar scissors. Ready for this? Look at that. Just with like literally scissors. Like I've been able to scratch the crap out of these. Can't do that with these. Look at that. See, that just wipes right off. That just wipes right off. Going. I mean, that just wipes off. Like that, an actual scratch versus, I mean, can't even see it anymore. That's how hard these are now. They actually originally tried tapping the threads with a hand tap after, and they couldn't. So they had to spark erode them. And that just goes to show how hard these actually are. And of course, they did the diamond test. Now I'd like to talk about some of the changes I made. So the first change you can see that I made, the spline only extends as long as it needs to. It doesn't need to go past its engagement, which is about here. There's no point, because you're just cutting material out of there and making it weaker there. The other big change I made is, you can see how this is one diameter? This one's just one diameter. Well, that's a poor design, because right at the end of the spline is where all the stress concentrates. And that's why down here is where it twisted. On this one, you can see the spline actually sits on a larger outer diameter than the shaft. So those stress concentrations aren't going to be as aggressive right here where the spline ends. It also allows your shaft to be a smaller diameter, which allows it to twist more. You want an axle to twist as much as possible without yielding to your required input torque. So this axle can actually twist twice as much as this one, and it's going to act like a spring. It's going to twist, and then it's going to shoot you forward. The last change I made was here. You can see I added another outer diameter right there, and that is actually to center this inside of the diff so that it can't wiggle around. Before, this could actually wiggle around quite a bit, because the hole that it was going into was a little bit bigger than this, and it was just a mess. And I'm going to show that now, the difference in fitment. And obviously, we talked about this in the previous clip, but this spline is way better. It is way higher quality. It's cut way cleaner. And I was able to dial it into the exact freaking fitment I needed. I was able to 3D print spline prototypes and test fit them in the car so I can get a perfect fit. And I got the perfect fit spline. There's no backlash. Before this version, it had a ton of backlash in it. This has no backlash. It is the perfect exact fit for the differential. So some really big improvements. Nothing changed down here. A little higher quality machining. Nothing changed here. Nothing changed here. Pretty much just here and above changed, the important part. Now you're probably thinking, if you do 3D printing,
Well, wait, Matt, 3D printed splines, they warp and whatnot. Yes, they do warp, but there's stuff you can do to counteract that. And I'm not going to go into that because that's my secret sauce. But there are ways to get around that. And the 3D printed prototype spline that I printed and test fit it is pretty much identical to what was machined because of how I made some adjustments so that when it printed, it didn't distort or warp. So that theory works, which is really cool. So let's get these in the car, and I'm going to show before, and then we'll show after. And the improved fit is really awesome, and I think it's going to make for a much more stable rear. Right. So here's that diameter that I'm talking about in here, that second OD centers on, right there. So that's what that centers on. So let's test out the old version. So the issue with the old version spline fitment was my manufacturer, I had the spline spec exact, but I didn't specify a tooth thickness. I figured they would cut it to like a standard class 5 or a class 7 tooth thickness. That wasn't the case. The tooth thickness ended up being way, way too small. And you can see when I put it in, hear all that backlash? It's kind of hard to see. Hear all that backlash? It had quite a bit of backlash. See all that movement? Because the tooth is too thin than its counterpart. And when you push it in all the way, there was nothing to center this on that ID right there, so it can move up and down a little bit. And you can see all that backlash right there? So the spline fitment wasn't too good, and the up and down movement wasn't too good either, because when you would take off, you kind of hear these clunk up and down. It didn't affect seal fitment at all, because the seals have springs that can stretch and whatnot, but it just made some noise, and that extra backlash, probably on accel and decel, was causing some of that, see that like nicking, that galling right there, from that back and forth, because not only was this spline not hard enough, it was probably less hard than its counterpart, so that backlash was causing it to kind of just smack into the diff, and probably wasn't too good for the splines. Let's get the new version and we can see the improved fit. I have the new version pushed in, but just so there's spline engagement. And look, I can't turn it at all. There is zero backlash. You can see it's got a good fit. See how it's like kind of scraping against its counterpart? That's good. There is no backlash, no noticeable backlash at all in the new version, because I was able to dial the spline in perfectly using this new spline cutting method. And now I'm going to push it in. You can see how it still can go up and down a little bit because it's not centered on that new OD I added. Now with it on that new OD, look, there is no up and down, there's no side, there is nothing. No backlash, no up and down, just in and out. And you can see it's got a really good, nice tight fit. And that is what you want. That is what you want on a splined component. You don't want backlash, because backlash is going to create like a hammering effect, you know? And up and down movement, it's not bad, but it just creates unwanted noise. And you can see that's in all the way now. And no up and down, no backlash. Like, the fitment is just light years better. I want to say this one more time because I know there's going to be someone that's going to say, oh, it's the locked four-wheel drive that caused this. Locked four-wheel drive did not cause this. I've had these out multiple times. I had them out after launches with the viscous coupler. I had them out after launches running it four-wheel or locked four-wheel drive, after launching it four-wheel drive. I'm telling you, that last launch I did that twisted these, the amount of torque that was going to that rear was astronomical. With that car locked four-wheel drive, it is basically 80% rear-wheel drive, and all those fronts are doing are keeping you going straight. So locked four-wheel drive definitely did not cause this. What caused this is the annealed 4340 core, which is extremely soft, only 480 megapascals. The new one is about 1600 megapascals through hardened. The entire piece is 1600 megapascals, and the entire piece is about 50 HRC. If you look on this, Let me just try and see if I can find them. Here they are. See those? See those little nicks? What they do is they get a machine and it has a diamond on it, and they push that machine into it, and depending on how far that diamond goes in, with an applied force, you can calculate how hard the material is. So they did test these before they sent them out after manufacturing, and they are indeed 50 HRC through. They are very strong, hopefully very strong. We're gonna have to prove that, but I think they're very strong based upon the testing they've done and the manufacturing process that we took. So really excited. We'll get some more footage of these and whatnot, and talk about a couple other things before we wrap this video up. I also checked out the angle gear and other components, drained the oil. It was perfect. Looked in there with an endoscope, nothing, no issues. I'll probably show a little clip of that, or maybe put it in another video, but I checked everything out. Everything else is completely fine. The rear diff has great backlash. The front angle gear has great backlash. No issues with any of that. So, I mean, I guess that's saying something about my angle gear case, that if it can put enough torque to that rear to twist those, there's probably some decent torque going through it, and we can do some calculations to see how much torque it would take to actually twist these, and we can calculate about how much was going through that angle gear, and I think we'll do that next.
I want to show some torsion of shaft calculations. So basically what this takes is an input torque and the radius of the shaft. In our case, version 1, since the spline and the shaft were the same outer diameter, it's going to be 15 millimeter radius or 30 millimeter diameter. Shaft length, modulus rigidity, this is all set up. Modulus rigidity set up for 4340. But you can see if we had 2,000 pound-feet going through one of the flanges, that's a shear stress of 511, so that's a little bit above 480. So if we put 2,000 pound-feet through the old V1s, those would have yielded and twisted about 2 degrees, which is about what we saw. That's pretty crazy that we had 2,000 pound-feet per axle. It means there's 4,000 pound-feet going through that that angle gear. That's a lot of torque, and we're just getting started. Set up the calculation now for a shaft outer radius of 13, which is for version 2, because it necks down. And that neck down isn't for, that's not an engineered weakness, that's to prevent extreme stress concentrations at the end of the spline. Calculate it now, you can see our max shear strength went up because our shaft radius went down. But our V2s have a yield of 1,600 megapascals. So we're under half, we're just about at half now of their maximum torque capacity. So we can crank this up to 4,000. So each one of our stubs now can handle 4,000 pound-feet, a combined 8,000 pound-feet going to the rear. That's close to 10,000 newton meters, probably a little bit more. That's insane. So not only do we have a ton of torque going through the angle gear and through the rear, but these new stubs are going to be able to handle even way more, and hopefully that angle gear and the prop shaft, which is a high-speed, low-torque prop shaft, I know the rear will handle it, can handle it too, and the outers too. We'll talk about something I'm working on with the outers. I want to show some of the CAD model too. So here you can see what I was talking about, how when it's machined, it's not machined with the spline, it's machined just with the OD, and then the spark erosion machine is run down it to make the spline. Boom, spline. So this is the new design. I'm really happy with it. I spent a lot of time working on it, and I want to show a little bit of FEA too. Here's the FEA model. I'm going to ignore the magnitude of the torque I'm applying to it, and we can just look. See how there's not really any extreme stress concentrations here because of that neck down. And you can see all the stress is concentrated in this shaft right here. It's really not anywhere else. We can do a slice plane and kind of look at it. You can see there's really not much stress. And you can see how the stress is really just on the outside. The center is fine. That's why you can gun drill axles, just because all the twisting's on the outside. See how it's all blue here? That's why some people gun drill them right through the center to reduce their mass, because you don't need material in the center. thought I'd show this. I think FEA is really cool and I use it a lot.
Another thing that I'm working on in the background is I'm working on some outer stubs. Just in case the factory outers ever break, we're gonna have these on deck. This is a different spline. It's a 26 tooth and it's also a different profile. The other ones over there are 27 tooth. The inners are 27 tooth. They're a little bit bigger, but in order to make these just as strong, I would have to manufacture these out of a stronger material such as 4340M, or also known as 300M. But let's get these in real quick, and you can see those just smack in like that. And instead of using a nut and having a big thread, I'm gonna use the same style bolt that they do on the later P2s that bolts in to the center of the stub and then sets the preload and holds it in and everything on the wheel bearing. And then the bottom is exactly the same for the Volvo 108mm GKN CV. And you can see that just goes on there like that. So basically we'll have 2 of these CVs on each end if we ever need to. And that's gonna make for an incredibly strong axle. These GKN 108mm CVs are very, very strong. And also, fun fact, these axle shafts are actually the exact same as a Porsche 911 930. And you can actually get off the shelf 4340 or 300M upgraded shafts. So I basically have the ability to create 1,000 wheel horsepower capable axle in the rear, which is gonna be insane. Because if you think about it, you know, maybe 67% is going to the rear, and to have 1,000 wheel horsepower capable axle in the back is going to be absolutely nuts for launch and keeping everything together in the rear where most of the torque's going on launch. So just wanted to share that and show that that's going on in the background.
Hope you guys enjoyed this video. It was very technical and in-depth. Hopefully some of you guys like that. That's the kind of stuff I like, all the engineering and whatnot that goes into this build. Next video, we'll be putting everything together. I'm still waiting on some parts and whatnot, waiting on a couple things. I also made some changes to my CV boot adapters on the outers to fix that pesky frickin' control arm clearance. I finally fixed that once and for all. And I'm gonna share that next video, and we'll start getting this thing put back together and driving and boosting. And I also made so many other changes on the car that I video documented a bit, and we'll talk more about that next video because this one's getting a little bit long and I want to hopefully get back to more regular videos.